Welcome to Manufacturing Processes, Machining and Machine Tools lectures by Professor Joyjeet Ghose. This is the fifth lecture of a series of lectures. This lecture will be on types of chips, tool wear and tool failure. He will be discussing about the different types of chips formed during metal cutting, the mechanism by which different types of chips are formed, types of tool wear, their causes, types of wear mechanism. This lecture also discusses the tool failure criterion. So, do not miss and watch the full video. For the next video in the lecture series, please click the suggested video link above. You may also click on the playlist at end of the video to access my videos. Please subscribe this channel and yes, do not forget to like and share. Also click on the bell icon to receive instant information of new videos uploaded. Thank you.
Hello friends, welcome to lecture 5. In this lecture, we'll be discussing about different types of chips, and we'll also discuss about how tool fails and what are the mechanism by which tool fails and what are the different types of tool wear. So these are the topics that we'll be discussing in this lecture. So let's not waste any time and go straight to the lecture. So chip formation, how chips are formed. So this we have discussed in the previous lectures, how chips are formed. As the tool moves ahead, the area or the zone ahead of the tip of the tool gets severely stressed. And when this shear stress becomes more than the shear strength of the workpiece material, the material will shear plastically over the tool face and flows over the face of the tool. Now this chip is considered to be the deformed material, and below the shear plane is the undeformed material. Now this shear plane remains attached to each other and appears as a deck of curds sliding over each other. That is particularly happens in case of a ductile material. Now what are the different types of chips that are formed that we are going to discuss here? We are going to discuss the three basic types of chips: discontinuous or segmented chips, continuous with built-up edge. Now in my site there are several videos of how chips of each of these chips are forming. You should go through these videos and they will understand by seeing the actual videos how these chips are formed. So this is a discontinuous chip. You can see it is a serrated chip. Separate pieces of chips are flowing over the tool face. And this is a continuous chip, and this is a chip with built-up edge. Continuous chip with built-up edge. This is the actual diagram. This I have taken from the book Donaldson. And here, this is a discontinuous chip. You can see the shear plane are fractured here. So this is for a brittle material. For a ductile material, you can see a continuous chip is formed. This is the tool. This is the tool here. And this is the tool here, but you will notice that there is a false cutting edge. This is the false cutting edge that is occurring, and this is a continuous chip that is flowing. Now this false cutting edge is basically nothing but the workpiece material being welded to the tip of the tool and forming a false cutting edge. It keeps on growing, and after a critical size it fractures. So this is highly unwanted. So this is a continuous chip with built-up edge. We will discuss in more details in the next few slides. So these are some of the chips. This is continuous chip. This is discontinuous chip. This is again a continuous chip. It's tightly curled. So different types of chips are shown in this book. Okay, we'll start with continuous chip. How these continuous chips are formed? The most important thing is that it is continuous chip means the chips is intact, that is, it is not fractured, and it flows continuously over the face of the tool and forms a ribbon type of chip. Okay, now how these chips are formed? Remember, this most important thing is that for the continuous chip to form, it has to be a ductile material. And not only if it is a ductile material, under certain conditions, then only this type of chip will form. ductile materials like mild steel, copper. Now this the feed has to be fine feed. Fine feed means low feed, and cutting speed should be high. That is very important, and rake angles should be large so that the cutting edge is keen and smooth tool face. And of course, it is better if it is lubricated. That means cutting fluids are applied between the tool and the workpiece. So these are the conditions under which continuous chips are formed. Although we want continuous chip to form, now this formation of continuous chip or curling of this chip, sometimes long chip, can create accidents. So we want continuous chip to form, but normally we use chip breakers to break the chips after regular interval so that it does not get entangled with the tool post, or this hot chip may lacerate the hands of the operator. So even though we want it, we normally break it after a certain point of time using chip breakers. Chip breakers is not included, so I am not going into details of the chip breakers, but you should know that although it is favorable or wanted, we have to break it because this long continuous curled chip can create problems during the machining. Okay, now continuous chip with built-up edge. As I've already said, you can see here in this figure, this is actual figure, this is a micrograph here, and this is a tool, and this is the workpiece, this is the chip. You can see the shear planes, these are all shear planes which are moving up. It's continuous chip, it's ductile material, but here you can see this workpiece material is welded to the tip of the tool and forms a cutting edge. Its cutting edge should be like this, but it is now like this. Okay, now it forms a false cutting edge. Now how this happens? Under certain conditions, the stress becomes so high that the temperature also increases. Now this high stress and temperature resulting in a situation where the workpiece material, as it is seared, it gets welded to the tip of the tool because of high pressure and temperature. It gets welded to the tip of the tool, and this phenomena continues and until a critical size is reached. When this critical size is reached, what happens? After that, it fractures. Now, problem occurs when it fractures. When it fractures, the pieces, fractured pieces, may get deposited on the machined surface and spoiling the surface finish. So, therefore, it is highly unwanted. Now, what are the conditions under which this can happen? Obviously, this happens when we are machining ductile materials. Under certain conditions, like when the cutting speed is excessively low, feed is excessively high, we have a very small rake angle and lack of lubricant. You can see all these factors are contributing to high pressure and temperature. See, small rake angle means the pressure increases, lack of lubrication means friction is high, temperature is high, so there is no coolant here, and cutting speed also resulting in the same thing. So all these factors results in the welding of the workpiece material on the tip of the tool, resulting in a formation of a false cutting edge, which we call a built-up edge or BUE. So this is highly unwanted and should be avoided while machining ductile materials. Okay, now discontinuous chip. Obviously, discontinuous chips are segmented chips which are in which the small pieces of chips flow over the face of the tool. Now, when I say small pieces, what happens? How these small pieces of chips are formed? Now, when you are machining a brittle material, what happens? In brittle material, you cannot give much deformation. So, after a little deformation, it fractures. Now, normally, as you go plow into the workpiece material, see here there will be deformation. After little deformation, fracture will happen here, and this fracture will travel and reaches the surface. As it reaches the surface, it separates from the workpiece. Now, by the time it separates, this length moves up the face. So, a small length is existing for the continuous chip. So, what happens as we are deforming it? It fractures initially at tip of the tool, near the tip of the tool of the workpiece. It fractures, and this fractures travel slowly to the surface and get separated from the workpiece material and moves in the form of discontinuously over the face of the tool. Now this will happen in case of ductile brittle material and under conditions like greater depth of cut, low cutting speed, small rake angle. So these are discontinuous chip. So these are the three basic types of chips: that I have discussed. So with this, we'll move on to tool wear. It doesn't matter what type of cutting tool materials you are using, it will wear. It will wear because there is a metal to metal contact with the chip and the work. Very high stress is acting and high temperature. Also there is temperature gradients and there is stress gradients. So it doesn't matter what type of tool you are using, what type of coating you are using, tool will wear. And our objective is to extend the life as much as possible or to reduce the wear as much as possible. So wear happens because of many reasons, and there are different types of wears. Two of the wears that we'll be discussing is the crater wear that happens in the face of the tool, and the flank wear that occur in the flank side of the tool. This is flank wear or the clearance face. This is the crater wear. So before we discuss the wear, we should understand how wear actually happens or what are the mechanisms for tool wear. So these are the four mechanisms by which tool wears. First is abrasion. Abrasion occurs at a relatively low cutting speed, or you can say low cutting temperature, where the hard inclusions in the workpiece plow through the tool face and flank surfaces. So then the tool wears because of abrasion. Now adhesion already I have discussed, mainly happens due to ductile material. Under certain conditions, faulty machining conditions, this material gets welded to the tip of the tool and forms a built-up edge and adheres to the welded, or you can say adheres to the tip of the tool and forms a false cutting edge called built-up edge. And after critical size, it fractures, and when it fractures, it takes a part of the tool also with it. So that is another wear mechanism. And still at a higher cutting speed, diffusion takes place. Now diffusion takes place at a high cutting speed. What happens under diffusion? Atoms from the hard cutting material or cutting tool material diffuses into the soft workpiece material, making the workpiece material hard and simultaneously making the tool material soft. So okay, it's a two-way process. Similarly, atoms from the soft workpiece diffuses into the hard tool material and making the tool material soft, and similarly vice versa, this process takes place and it will ultimately wear. So this type of wear is called diffusion wear. And lastly, at very elevated temperature, normally at a very high speed, temperature is very oxygen. So they react with this oxygen from metal oxides. The metal oxides are highly brittle and can erode very easily. So such type of wear mechanism are called oxidation. So a particular wear can happen by combination of one or more wear mechanism. So these, but all the wears can be the causes can be attributed to one of the four wear mechanisms or more. So first we'll discuss crater wear. Crater wear is not a major wear. Normally tool does not fail by crater wear, but if crater wear takes place, it can result in a catastrophic failure. Now what is this crater wear? It basically forms a crater on top of the face, tool face or rake face. So how this happens? This happens under high cutting speed, and when cutting tough material, this type of wear can take place. Now what are the wear mechanisms that leads to this? This is mainly caused by diffusion and adhesion. So when built-up edge fractures, it takes a piece of tool material from the face of the tool and forming a crater. So that is wear. And diffusion. And diffusion mainly takes place, let's say in certain condition when you are machining with, let's say, tungsten carbide, and that tungsten carbide is basically made of WC and cobalt binder. Now WC and the cobalt binder, this is high affinity for carbon. Now as it is moving here, so carbon diffuses, carbon from the tool material diffuses into the soft workpiece material, leading to making it softer, and it plows and crater is formed. So this is called crater wear. Normally tool does not fail by crater wear, rather it fails by flank wear, as has been shown here. We will see in the next figure. So what is this flank wear? Flank wear is the principal wear by which tool fails. a normal tool fails. Now, it is the wear that occurs in the clearance face or flank face. So it occurs in this cutting edge here and extends to this side also slightly. Now, if you clearly look at cutting or this flank wears, you can see here there is a deep cut and deep mark, and there is another deep mark here. So these two are caused. This is caused by touching here the nose. This is wear of the nose. So I am not interested in the wearing of the nose, and this is the depth of line cut or depth of cut line. So I am more interested in this zone. So there will be wear in this zone, and the average wear with the length of wear from this length from the top surface to this average length is called the VB, or called the length of the wear land. This is called the wear land, and where maximum occurs is called VB max. That is the VB max. Now, now what causes this? This is caused by the rubbing of the newly machined work surface on the contact area of the tool. This type of wear occurs on all tools while cutting any type of work material. Flank wear begins along the leading edge and generally moves downwards away from the cutting edge. So it starts from here and moves in this direction. Edge wear is also common, known as wear land. So this is flank wear or edge wear. We will call it as a flank wear. Now it has been plotted. If you plot the tool life and the wear, this distance here, so how much it is wearing with time, you can see initially there is some rapid wear, and then it is a steady state zone, that is uniform wear, and then at the end it may be a very sharp progression of the flank wear, resulting in a catastrophic failure. This is a rapid and catastrophic zone. So ideally you want to change it somewhere around here. So when the flank wear reaches this level, then you should change the tool or replace the tool. So this curve is very important, representing the flank wear in three zones: rapid wear, initial rapid wear, uniform wear, and the rapid catastrophic failure wear leading to catastrophic failure. Okay, now two terms here. In case of Scatteraware, this depth of crater is called KT, and the distance from which this tip is called KM. So two terms are important in crater wear, and this term is important in flank wear, VB and VB max. Okay, now important, this will discuss in the next lecture, but let me introduce this concept to you. So if I plot the flank wear curves of a particular tool and workpiece material for different cutting speed, the curves will look like this. Now notice that this curve is for cutting speed 100 meter per minute, this curve is for 130 meter per minute, and this curve is for 160 meter per minute. And we will say the tool has failed at a flank wear of 0.5 mm. Now for each of these, if I draw a line for each of these, if I drop here perpendicular, so this comes out to be tool life to be 5 minutes, and this comes out to be tool life to be 12 minutes, and this comes out to be 12 life to be 41 minutes. So we have seen, we can see here and notice here and can interpret from this curve that if the cutting speed is less, the tool life is more. If the cutting speed is more, tool life is less. So one of the major parameter on which tool life depends is the cutting speed, and it is inversely proportional. This was a major finding of Taylor, and this will be discussing in the next lecture. So this was based on the tool life. This is flank wear. And how do we consider the tool has failed, or what is the tool failure? When the tool no longer performs its desired functions, that means it is not cutting properly, then we can say that the tool has failed. Now, how to come to a conclusion that the tool has failed? How to quantify this? Normally, there is a tendency by the operator is to overuse the tool, because that will lead to less expense for the company and he will get bonus. And And in order to increase the tool life, the operator, what he does is that he may use it slowly. Now if there is a pressure from the company to increase the productivity, then what the operator will do is that he will use it at a very high speed, and the tool life will decrease. So there has to be a criteria based on which you decide what is the tool life. Now there are several criteria. First criteria is based on flank wear that I have discussed right now. Now I also says that if the flank wear of a tool has VB is 0.3 mm or VB max has reached 0.6 mm, then we should reject the tool and we should continue with other tool. So this is the criteria using flank wear. Now there are certain criteria using criterion also. Two persons, Optich and Weber, I also recommend is that the tool has failed by criterion if KT I have discussed, this is the depth, this depth of the crater is called KT. If KT is 0.06 plus 0.3 F, where F is feed in revolutions, then the tool may be considered to be failed. And two researchers, Optich and Weber, they have found that if the ratio of KT and KV is between and the maximum permission value of this should be between 0.2 to 0.4, otherwise there will be a catastrophic failure. And also sometimes because of certain faulty conditions, the tool may plastically deform. If the tool is plastically deformed, you cannot use it anymore. So the tool has failed obviously, and if there is a breakage, then tool has mechanical breakage, that the tool can be considered to be failed. And it can fail because of combination of flank wear and criterion wear also. So this is how the tool has failed. So these are some of the other wears. We will not go into such kind of wears here, but our discussions was mainly limited to criterion wear and flank wear. So in this lecture, we have discussed what are the different types of chips: continuous chip with built-up edge, and discontinuous chip. Then we have discussed different types of wear. We have discussed wear mechanisms. These are the things that we have discussed in this lecture. Hope you have liked this lecture. Thank you for patiently hearing and seeing this video.